This will be a slightly different talk for for two reasons. One is, as previously mentioned, I don't do most of my research on poultry. I'm kind of more a plant imager, but what I hope to show in this presentation is that these are all connected fields, and it doesn't really make as much sense to silo them as much as we do, and that maybe this is one of these things where we can cross and learn from each other as we go. So, before we get going, I would like to get a show of hands from the audience. Who here knows something about spectral imaging? Okay, who knows a lot about spectral imaging? Cool. So the good news is that I started this presentation with a quick overview of what is spectral imaging. So we'll start with the idea of conventional imaging. Everyone has a phone. It exists in your pockets. Maybe you have a Nikon or something nice like that. Cameras work by taking light, sending it through a lens, and then imaging it normally on a CCD. That can make a picture. The pictures that we normally get are 2D. They have a length and a width. And they're either in monochrome or they're in color. This is 90% of what happens when we talk about imaging and imaging technologies, right? And this is where all of the really big algorithms and image processing that you see has been built on over the last 30, 40 years, right? Everything from just, if it's a bright thing in the image, highlight it, to more complex things like all these new neural nets and CNNs that you might have seen online. They all work on traditional imaging. Two dimensions, length, width, and either one color or three colors if you're talking about RGB. That gives you a lot, right? If you take a picture of something, then you can see where it is, how big it is, shape, stuff about it. But what you don't get is more intrinsic. Like, what is it made of, right? What is actually the thing that you're looking at inside of that image? For that, you normally need to know kind of more in-depth information, right? This is where chemical analysis comes in. Take something, grind it up, and then figure out what are all of its little bits and pieces. But there's another way that you can do that with light, and that's using spectroscopy. So spectroscopy is a very old field. Basic idea of it is that light is not white, it's a rainbow, right? Lots and lots of different wavelengths, and depending on the wavelengths of light, certain elements or molecules will absorb or emit that light, right? So in this case, this is the spectrum of the sun, right? And if you heat up sodium, you can see it shows 2 or 3 different bands. If you're just looking at any spectra in space and you see those 5 bands, that's sodium, right? It's a marker for what's actually inside the object, and it can tell you more about what it is without having to grind it to pieces. The spectrum's huge, right? We have waves from the size of football fields to waves that are really, really, really small, smaller than an atom, right? In all of these cases, technically, we could image with them, right? But as you get with larger and larger wavelengths, you need larger and larger detectors. So you're not really going to be making a giant CCD to capture radio waves. That would be insane. And in the same side, if we go too low with things like hard X-rays, it's actually so much power behind the wave that you kind of, you blow out the detector. So in reality, we really talk about imaging vaguely in this field. This is where the strength of the wave and the length of the wave is reasonable to make a picture with. But there's a lot of stuff that exists in this range. Obviously, visible. RGB cameras, red, green, blue, take light from that region. But then you also can move into the invisible. You can look into the infrared a bit. You can look into the ultraviolet. And soft X-rays, which is where if you go to the doctor, that's the kind of X-rays you get. And what's important is that in this wavelength range, things that constitute biological matter absorb light. So things like water, things like proteins, chlorophyll, fat, all of these have at certain wavelengths of light that characteristic absorption line. So without ever having to tear up something, you can monitor things and figure out what are they made of. Now, spectroscopy is normally done with a point sensor, right? You take a little white, like a fiber or the end of an optic, push it against a thing, measure the light that comes off of it. But if you put together spectroscopy and imaging, you can do spectral imaging. The way this works is many different ways, but the original way that it was done was in space. We had a bunch of cameras on a satellite. Each camera had a different piece of colored glass in front of it, only let in one wavelength of light, and then as it flew over the Earth, it could reconstruct an image of what it was looking at. From that, you had an image at each individual wavelength, and so if you took kind of a cross-section here, you could get the actual spectrum, or you could get an image. It started, of course, with the satellites, but then we got smaller and smaller. This was in the 80s. By the 90s and 2000s, we had cameras on the ground that could also do this. I'm going to take a quick aside, though. This conference is called Hyperspectral Imaging in poultry science. Technically, I'm not going to use the word hyperspectral. With respect to my fellow presenters today, it's just a thing that in Wageningen we're not doing anymore. The reason why is that there are lots of ways to kind of define taking multiple images at multiple wavelengths. The word hyperspectral has become hyped, pun intended. There are now thousands of publications, each with their own definition of what hyperspectral means, and it's becoming kind of a useless word. I think last year there were 3 papers that I saw that were using ultraspectral. It doesn't mean anything, right? Spectral imaging or hyperspectral imaging or whatever term in front of spectral imaging you see just means different wavelengths of light, different images, and then that's it. So just throwing out the nomenclature halfway through my talk, but there it is. Okay, what does spectral imaging look like? This is a kind of a representation of what you get when you take a spectral image. You have a stack of images, and each image is at an individual wavelength of light, right? So maybe the top one is at 650, which is vaguely red. The middle one is 520 nanometers, which is vaguely green, right? But each individual image is slightly different from each other because they're only looking at one wavelength. If you take a cross-section and look at the X and Y here, then you can do image processing, right? Here you have a grayscale image. You can do segmentation. You can take out individual leaves on a plant. You can look at individual eyeballs on a fish, right? Whatever you want can be done with all of that image processing that has already been developed over the last forever amount of years. But the advantage here is that if you go the other way and you go down, every pixel of this image cube has a spectra behind it. So say you start and you segment off this plant and you say, these are the leaves. You know where the leaves are. You can then look at every single pixel on that leaf, right, and see exactly how much the chlorophyll in that leaf is absorbing light. So you can actually look really deeply on a spatial level and see how things are changing in time. This is really different from the way that we normally do this, used to do this, because with spectroscopy you have to take a point and look at one point. Here or if you're grinding it up, you grind up the whole leaf, right? And you get an average value. So this is a way to get standard deviation. It's to see how things change. You can take lots of pictures over time. You get functional and temporal data. All the things I just said. I forgot I put the slide here. So it's non-destructive. You don't have to tear up whatever you're measuring. If it's a chicken in a pen, you can keep taking the same pictures of that chicken over the course of its life. You don't have to kill it until it's time to kill it. It's fast. It's a picture, right? Traditionally, we talk in RGB cameras about taking an image in like depending on the ISO, of millisecond or something. These cameras are slower, but they're slower to like 10 milliseconds, maybe 50 milliseconds if you have like a really big one. So not really slow. And they provide functional data. Functional data is, as a biological thing is living its life, its spectrum will change as the biology inside it changes. Actually measuring functional changes in organisms is huge and something that is really hard to do with chemical data because you have to grind up the thing, which makes it stop living, right? So this technique that's, I think, one of its most strongest points. But of course, it has disadvantages because everything does. And in this case, if you look in the literature, there are really three things that are bottlenecks for spectral imaging. The first is overparameterizing. Here is a spectrum. You can see that there are these depressions, right? This is reflectance. So if the light goes down, light is being absorbed. Light is being absorbed here by water. And you can see that there's this is water, this is water, that's water, right? It makes 3 different absorption lines, but I have 112 different bands here that I could make an image out of. So what you really quickly get into a problem with spectral images is you'll overparameterize. This wavelength and this wavelength are highly correlated. They're both being absorbed by water, but you'll see a lot in literature and in like talks that people give. They'll say stuff like, I've determined the water wavelength. It's this one, as opposed to my prior paper who said it was this one. It's the same thing, right? But you have to break down on this overparameterization before you can actually do good spectral imaging. That normally just means taking your giant spectrum, focusing on certain wavelengths where you know there should be something chemical that you're looking for, and then removing just that light and binning it together. Second problem is reduction. This is ginger? Milk powder. Ginger. Powdered ginger in these little trays. They came from different areas of the world. Yes. This was a study that a student did. And in each of these, what they wanted to show is that, oh, this ginger is from somewhere else. I can find these different wavelengths that matter. But in order to do that, they took in each cup, masked it, and then took an average. And at that point, you've lost that image data, right? And you'll also see this a lot in literature. People will use spectral imaging as just a fancy spectrometer, right? A way to just take spectrum from one thing. And you can use it that way, but it's throwing away so much data and variability here. If you wanted to, like, you could look at how spectrum changes over the grain size here, like a lot of different cool stuff. But it's normally used in this manner, just because it's kind of easier. There is a third one, which I hid behind the graph, and that's data. This is 112 images shoved into a single image. The data is much bigger than a normal picture. And if you're taking lots of them in time, it's a lot of data. Like really quickly terabytes of data. So knowing what data to keep and what data to throw away is vitally important. We have this thing in Wageningen called the National Phenotyping. We have a system that is made to phenotype a plant over its entire life cycle. Every day, 2 spectral images are taken. By the end of a month, that one plant in a greenhouse full of plants has over 200 gigabytes of images on it. We very quickly realized that that wasn't possible. And so now we do a lot of pre-processing basically as soon as the image is taken. But yeah, there was a small moment of panic where we watched us approaching like a petabyte of data, and we were like, oh God, oh God, oh God. So, all right, that's spectral imaging. But the question then is, with that kind of background, where can you use this? And the answer is everywhere. If you want to look for anything chemical or biological, spectral imaging can give you that data without much work at all, right? It's taking pictures. You don't have to you don't have to grind anything up. You don't have to wait a long time for information to come out. You can just take a picture. And you see that in the scientific literature as well. If you look at papers that are coming out about spectral imaging, it's across the board. It's agriculture, engineering, physics, and astronomy. Has to be astronomy, by the way, because you can't touch stars. Computer science, material science, all of them. Any field where you need to look at chemicals, use spectral imaging. That includes poultry. So this is actually, there have been studies in the past about using these imaging systems, right? All the way back to 1996, which is the first one that we could find, where you can use this spectral imaging for trying to figure out where like tumorous bruises are on chickens. And it's developed up from there. You can still use it for meat quality design. I've heard several people talk about the woody breast and the spaghetti breast in this conference. Those are caused by deformations in the breast tissue, right? You should be able to see some kind of signature from that. So, and in addition to that, even though chickens are fluffy and full of feathers, longer wavelengths of light can penetrate a bit, and you can actually see signatures from the health of the chicken as well. So you can use it for quality on the end of the chicken's lifetime, but you could also use it in the middle when the chicken's alive. You could use it at the beginning when a chicken is in an egg. Eggs are vaguely seed-like, and I know that you can use spectral imaging for seeds to find viability. And there was actually a paper I read last night about using the infrared to measure the amount of fat and water inside the egg itself. That tells you something about the sex of the chicken. So you can use it throughout the chicken's life. But of course, I do a lot of stuff. So I'm going to just point out some additional applications that we've done because I hope they inspire you into something that you guys could use as well. Plant quality. This was a project we did where we took spectral images of tomatoes and their leaves. And for each of these, we after we took a bunch of spectral images, we took them away and did chemical analysis. We ground them to their individual parts and ran every single different chemical that makes up these two organs on the plant. You can see we use the infrared, we use the visible. The spectrums don't always look the same, but that's because it's a living thing, right? Some leaves have more chlorophyll, some fruits have more sugar. 5 minutes? No? Okay. And what we found is there's tons of information you can pull out. Some of this, like starch and sucrose and fructose, all of those are direct measurements. If you look at the spectrum, you can see a dip. That dip is the absorption of sugar. Some of them are secondary, right? Things like the magnesium and the potassium. We don't actually see a dip that says this is magnesium, right? But what we do see is the chlorophyll content rises and falls with the amount of magnesium in the plant. So you can look at secondary effects, right? You can look at how the plant is uptaking these things. But it's not a perfect measurement for everything. As you can see here, natrium, salt, there is no signal, right? You have to have a signal to be able to see these things. But if they exist, you can get a lot of information with a single image. That's using it as spectroscopy, but again, it's a picture. So taking that information that I just showed you, we could then go backwards and map the amount of chlorophyll in a leaf, map the amount of water in a leaf. Over the course of a day, there was a video that wouldn't play. You could watch the water flow in and out of the leaf through transpiration, right? Uptake through the leaf, out. That's carotenoids, the orange color of leaves. So you get a bunch of really cool information. We were using this to try to find tip burn, which is a disease in lettuce because we've bred them to be too big. And so now the ends of the lettuces die and turn brown, which makes people not want to buy them. So I'm sure there's some allegory for chickens there, but But this is all the research side of it, right? Spectral imaging is currently in use in industry, right? You can use it in a lot of different ways because A, image processing is already out there. Everyone's using computers. Everyone's using image processing. And adding additional wavelengths is kind of the next step forward, right? We already have the infrastructure in place. It's updating and upgrading and making the algorithms better. We work primarily in agriculture. Agriculture, in our case, is things like orchards, looking at fruit trees. It's inside greenhouses, looking at tomato and cucumber vines. And it's open field crops where we fly drones above them, right? In all cases, though, it's the same concept as before. So this is a picture here of an apple leaf. This is a very sick apple leaf. And to you and me humans, it's very hard to see, right? This is the same image where I've selected the 3 prominent bands that differentiate the apple disease from the actual healthy leaf. And you can see suddenly dot, dot, which are the first signs of apple scabs, right? So even if we just use the spectral imaging to make a 3-color image, this is just those 3 bands that are the best, at that point, this is a high contrast image. You can use image processing and do much better. This is mildew. Same idea. Mildew is kind of a lightish green color on a leaf because the mildew sits on the back and sucks out all the nutrients. Young leaves look the same color to us humans. You can really only find it because it makes this specific pattern. Change the color, select the highest wavelength bands, and use image processing. Plants are primarily chlorophyll, but animals are not very chlorophyll-full. But they do have their own signatures to them. So we also work a lot with the North Sea fishery fleets, and that's normally herring and mackerel, which is spelled very correctly up there. In this case, what is most important due to regulations in the North Sea is that they only catch a certain amount of fish, right? If you overfish the North Sea, most of Northern Europe is going to have a big problem. So it's very important to fishermen that the moment the fish come in, that they are sorted into whether or not they are bycatch and thrown back into the ocean, or they stay on the ship and they get sold for later. That means that in this case, what they wanted to do is see, as soon as the fish hit the fishing boat, can we determine how much fat is in that fish? Higher fat fish, paid a lot of money. We did this for 2 different species, and if you look here, remember I pointed this out before, 1, 2, 3 are the water bands, but if you notice here in the middle band, there's this weird little like hump. That's fish oil, fish fat, right? And you can see that it exists both in mackerel and in the herring. So it's the same signal, different fish, same signal, right? And if we use this analysis and run it through, what we can do is we can show that you can actually determine the amount of fish fat per fish, right, without ever having to. Right now they take like an electric probe and shove it against the side of a fish and check the flat location. But this is just on a line, take the picture, hopefully goes down the line and goes back into the ocean. We're not there yet because the North Sea is a terrible place to put a camera, but we're working on it. Yeah. Fish fat is fish oil, but you know what else is fat? Chickens. Same 2 lines, right? So this is the same idea as we had before. This is a project that I'm currently running with Sarah Erasmus, who will be talking later. But it's the same concept. Poultry breasts are made up of they're very complex and more complex than like a plant, but you can individually figure out each of the components that make up that chicken and poultry. We were looking primarily, again, at fat for this project. So here are the 2 fat lines. Again, you can see the little double, I've highlighted them for you this time. This is the 3rd fat line that we determined. It's right at the very edge of my spectral image. We can take the actual image itself, segment it, You can do all the image processing, and then we can go on the backside and actually figure out how much water, how much protein, how much fat is in each chicken. So that's how it kind of all comes back around to you guys as well, right? These techniques that were developed in space using satellites are exactly the same stuff that we can use in every different field that I've just described. We're all biological. There's an extra slide here somewhere where you can do this on humans for medicine, but I didn't want to talk about that. So what's next? Specifically, what should be next for us here in poultry? I can kind of think of 3 ways to move with this. The first is 3D. It's very easy to take a 3D image nowadays. Surprisingly easy. So if anyone has their phone on them, you can actually make 3D images just using your smartphone nowadays with this algorithm, with some algorithms that they have inside of it, right? 3D data goes right at the end of your spectral data as another wavelength, and now you have a 3D spectral image, right? You can see form, you can see shape, you can see chemistry on a voxel level. That's really exciting, right? Because if you can do that, the steps that we're making towards digital twinning, which is this fun catch, super cool phrase that everyone's using nowadays, gets much easier, right? Because if you have a 3D representation of a chicken, then, and you can watch in real time as you take images of it, right? How it develops, how it flows, how its nutrients are moving around, you can actually get much closer to a real working computer model, one where you change things in real time and see how they go back and forth. We're doing it for sugar flow. Sugars come from leaves, then they go to the rest of the plant, right? Some of it goes to fruits, some of it goes to the roots, some of it goes to new leaves, but we're starting to get to the point where you can trace, as the sugar stops being carbon dioxide and starts being sugar, where it goes through the plant, which I'm very excited about that. And then finally, non-controlled lighting. The problems right now with spectral imaging is it has to kind of be in a box where you know what the lights are. Neural networks, AI, those things can be used for analysis. They're much better used with spectral imaging for how to make images work in multiple places, right? So that you don't need a special box for your camera, so that you could set it up outside and hit a picture and get a really good image off of it. Those are my feelings, at least. So in conclusion, I think it's good. It's a good technique. You guys should look into it. It's fun. But if you do, look across the board. Don't feel like you should only look into the poultry research here. When it comes to spectral imaging, the wider the breadth, the better the breadth, right? So if you look from space to agriculture to material sciences, it's all the same techniques, and they can all be very useful in working in your own field. And then once you got it, it's not the last step, it's the first step. Pair it with a bunch of other techniques, and I think that it fits well in a full line for these kinds of things. And that's the end of my talk. And I think I have time for questions. Oh, wait, I have to acknowledge everyone. Shai, thank you. Brian, thank you. I'd like to thank Patricia, Sarah, thank you, and all of the people who paid me money. Now we're done.